Do you think math is useless? Like, who would ever need to use calculus and algebra in real life? Gamers, that's who. Do you want to be a BTD6 pro gamer? Then what you should do is watch a video titled The Mathematics of Banana Farms. Bloons Tower Defense 6 is a video game where you use monkeys to keep the evil Bloons from reaching the end of the track. What's at the end of the track? No idea. Do Bloons eat brains? Most monkey towers shoot darts or straight up missiles at the Bloons to pop them. But how do you get monkeys? The game gives you cash when you pop a Bloon. But if that's not good enough for you, greedy, but you can plop down banana farms, which generate money over time. But there isn't just one banana farm. No. You can spend more cash to upgrade banana farms to produce more bananas. In other words, there is a plethora of banana farms to choose from. The banana farm with increased production, valuable bananas, banana research facility, Monkey Wall Street, unpaid monkey interns. If you're like me, you probably wondered, why are we spending cash to get more cash? Does it make any difference? Is one of the banana farms the best one? Well, I'm glad I asked because that's what the video is about. In this video, we'll tackle the question, which banana farm is best? We'll analyze the problem and come up with banana farm goodness metrics through trial and error. You'll be taken on the same mathematical journey of discovery as the greatest mathematicians of history, except we are studying a game about monkeys shooting balloons. We'll find that the banana efficiency is a good metric for most banana farms, but if you want to reinvest some income towards buying more farms, we'll need to use the banana compound efficiency instead. On the way, we'll discover the fundamental theorem of bananas and the monkey bank theorem. No, this is not a parody, this is a serious math video. Like any good math problem, we need to first define the, I'm keeping that take. To answer the question, which banana farm is best, we need to first figure out what it means to be a good banana farm. Is it how much money it generates? After you plop down the banana farm, it starts generating money every round. As self-respecting mathematicians, let's use a letter to denote the income generated each round, G. If we look at this spreadsheet I made with the G value of every banana farm, you have no idea how long it took me to make this sheet. Why are you so bad, ChatGPT? And don't get me started on Gemini. We can see the banana central with valuable bananas makes the most money, a whopping $7,500 per round. So that means Banana Central is the best farm, right? That was a short video. Of course not. Although Banana Central makes a ton of money, it costs more than your mortgage to buy. So clearly, how good a banana farm is depends on both its income and cost. Let's denote the cost of a banana farm by C. Why does the cost matter? Because if you had $140,000 to buy Banana Central, you could have also used it to buy an army of normal banana farms. With this in mind, can you think of a metric to determine which banana farm is best? A good way to take into account both income generation and cost is as follows. You're given a huge amount of money to buy as many banana farms as you can. Which type of banana farm generates the most money per round? For example, with $20,000, I can buy 16 vanilla banana farms, or 8 valuable bananas, or 1 central market. The 16 banana farms make $1,280 per round, the 8 valuable bananas make $800, and the 1 central market makes $1,120. Seems like valuable bananas isn't very valuable. This metric is a good way to evaluate how efficient a farm is. If it's cheap, then you'll be able to buy a lot with your starting cash. If one farm generates a lot of cash per round, then all the farms together also generate a lot of cash per round. We successfully took into account both income and cost in a way that is applicable to actual gameplay. It's worth noting this metric doesn't match BTD6 gameplay exactly. If you tried to buy $100,000 worth of vanilla banana farms, you run out of space to place them. You'd also get carpal tunnel. Expensive banana farms have more space efficiency than cheap farms. Also, I said we have a huge amount of starting cash. That makes the metric simpler to calculate, as we'll see later. But if you don't have enough cash to buy a Banana Central, then however cost effective it is, it's useless if you can't afford a single one. This problem would be solved if we could buy half a Banana Central, but alas, we have to worry about the discreteness problem. Cheap farms have more discreteness efficiency than expensive farms. Ignoring space and discreteness constraints, our metric is great at capturing the cost efficiency of banana farms. So let's define it formally. You're given S starting cash to buy as many of one farm as possible. Then after one round, check how much income we made. The number of farms we can buy is S divided by C. Well, it's not exactly. If our balance is not fully divisible by the farm cost, we'll have some leftover cash at the end. With $21,000, you can buy 16 banana farms with $1,000 remaining. But we're mathematicians. We don't care about pesky details like leftover cash. To make the remainder negligible, we'll make the starting cash huge. We will take the limit as S approaches infinity. As S goes to infinity, the number of farms is exactly S over C. Limits can get you out of all kinds of tough binds. The income of one farm is G, so S over C farms will make S over C times G dollars. This is the kind of advanced mathematics we do here. What is that as S goes to infinity? Oh, it's also infinity. Yeah, if you have infinite starting cash, then you also make infinite money each round. Didn't think of that. Oh wait, it's fine. We can cancel out the infinity by dividing the income by S. Our new metric for how good a banana farm is the income generated buying as many farms as possible, divided by S, as S goes to infinity. So now the two S's cancel out, and we're left with G over C. We'll call this value the banana efficiency, epsilon, because of course we made it a Greek letter. We're mathematicians. This makes a lot of sense. We can see the banana efficiency increases with more income per round, but decreases with more cost. We're basically measuring how much bang we get for our banana buck. So with a new metric under our belt, which farm is best? If we look at this sheet, the farm with the highest banana efficiency is the Monkey Bank with increased production, at more than 10%. Then we have the Banana Research Facility with valuable bananas at 7.4% and Marketplace at 7%. Next is increased production and greater production, and the Vanilla Banana Farm is not bad either at 6.4%. If you go all the way down, Valuable Bananas is actually the worst with only 4.3%, along with Banana Central, but what do you expect from a tower that looks like a minion? But what does this number represent? Often in mathematics, when you find a useful formula, its result has a nice interpretation. In this case, the banana efficiency is how much income you get for each buck you invest into the farm. But this number is actually more meaningful if we take its reciprocal, C over G. The cost divided by income each round is how many rounds it takes to make back what you paid for the banana farm. So if you buy a Monkey Bank, it will pay for itself in only 10 rounds. But if you buy valuable bananas, it will take 23.5 rounds. I'm starting to think valuable bananas is very bad value. Let's call C over G the banana payback, rho. We have now discovered our first theorem. The banana efficiency is the reciprocal of the banana payback, or rho equals 1 over epsilon. Let's call it the fundamental theorem of bananas. I really hope these names catch on outside of BTD6. Imagine citing the fundamental theorem of bananas to your company board to explain why you're opening a new factory. Problem solved, right? Monkey Bank is the best banana farm. I'll be accepting my Nobel Prize in the mail next week. If you've played BTD6, you can likely see the problem. Monkey banks are different from other banana farms. Instead of growing bananas every round, monkey banks deposit cash in themselves and generate interest every round. This then means their balances increase exponentially. However, the bank is capped at $7,000, so the overall cash generation is not exponential. Waiting more rounds after the bank is full will not get you any more money. You must empty the bank and start over. The optimal way to generate cash with the monkey bank is to wait until it's full or almost full, then empty it so we can go again. For a vanilla monkey bank, that's after 12 rounds. If you didn't get that, it's okay. BD6 is a super complicated game. It's like if Plants vs. Zombies and Sudoku had a baby and that baby went to UC Berkeley. The point is, when you use a monkey bank, instead of generating bananas each round, you only get to collect its bananas every 12 rounds, or 14 rounds for IMF loan. For the banana efficiency, this just means we need to update our definition to use the average income per round. G for the monkey bank is the income it generates in 12 rounds divided by 12. See here, it's the optimal time to withdraw money. But as the limit-loving mathematicians we are, we'll take the limit as the number of rounds r goes to infinity, then divide by r. This doesn't change any of our numbers. Monkey banks do still have the highest banana efficiency, but it makes our formula look extra cool with 2 limits. Unfortunately, it doesn't seem that this is the best metric, even ignoring space efficiency and discreteness efficiency. Monkey banks keep cash tied up for too long, while other farms have liquidity to immediately use the bananas to buy more monkeys. But what if you're a pro gamer who doesn't urgently need more firepower right now? Don't let that cash go to waste. Reinvest it into more banana farms. In the real game, you do not have some starter cash to buy farms, then sit back and enjoy the bananas flowing in. You buy a farm, then use its income to buy more farms, then that income to buy even more. If you're a true BTD6 fan, you'll know that this is the default strategy when beating bosses, because you basically need to suffocate the diabolical Bloon in cash. Okay, I tried very hard to get footage, but this week's boss campaign bans banana farms from being used. I'm sorry! Let's modify our metric to reinvest income into more banana farms. Now we are looking at how much cash you are left with after our rounds of reinvesting income into buying more banana farms. We still want to ignore discreteness, so we're still making starter cash go to infinity and dividing by it. And r is still going to infinity because the more limits the merrier. But this time, your income is going to grow exponentially, so having r go to infinity and dividing by r is not going to cut it anymore. Exponential growth trumps linear growth. The ratio will diverge. So what do we use as the metric? Seems a bit tricky. Let's just explore how this stuff works first, then we'll figure out the metric. Let's say the number of farms we buy is n. At the beginning, we buy n0 farms. Remember, we're taking s going to infinity. With large S, we can ignore discreteness, and n0 equals s divided by c. The income generated by n0 farms is s1 equals n0g, or sg over c. That's our starting cash for the next round, round 1. The number of farms we have by round 1, n1, is n0, the farms we already have, plus s1 over c, the new farms we buy this round. That's s over c plus sg over c squared. Then the cash we make in this round is s2 equals n1g, or sg over c plus sg squared over c squared, which factors out to sg over c times 1 plus g over c. We can continue this with round 2, n2 equals n1 plus s2 over c, and if we plug in and simplify, we get s over c times 1 plus 2g over c plus g squared over c squared. Then s3 equals n2 times g, which is sg over c times 1 plus 2g over c plus g squared over c squared. Applying this handy formula, you'll notice this is actually equal to sg over c times 1 plus g over c squared. And g over c is the banana efficiency, epsilon. So this is also s epsilon times 1 plus epsilon squared. If we do this for one more round, we find S4 is SG over C times 1 plus 3G over C plus 3G squared over C squared plus G cubed over C cubed. This factors out to S epsilon times 1 plus epsilon cubed. We're seeing a pattern. SR is always S epsilon times 1 plus epsilon to the power of R minus 1. That makes sense because each round the number of farms increases by a factor of 1 plus epsilon, and therefore the income also increases by 1 plus epsilon. The income you generate at round R still only depends on the banana efficiency. Oh wait, I forgot. In our calculations we were assuming that you generate income every round, but for banana banks we don't withdraw money until some number of rounds later. So that's a new property banana farms have. How long it takes until you can use the income. We'll call it delta. Before, each round we generate enough cash to increase the next round's starter cash by a factor of 1 plus epsilon. But now, we only generate cash every delta rounds. Everything else is the same though. So now we multiply cash by 1 plus epsilon every delta rounds instead of every round. On round R, the number of times we bought new banana farms is only R minus 1 divided by delta. The cash we start with is SR equals S epsilon times 1 plus epsilon to the power of R minus 1 over delta. Of course, we need to worry about R minus 1 not being divisible by delta, so we take the limit as R approaches infinity. I think you can start to see why limits are our best friend. So we have incorporated delta into consideration. What is our final metric to decide if a banana farm is good? Obviously, we don't want it to depend on the round number, R. Well, we could simply yeet R from the formula. Let's divide the rth round starter cash by S epsilon, then also take the R minus 1th root. We'll call this the banana compound efficiency, chi. That's another Greek letter if you didn't know. Plugging in what we found and canceling out S and R, we get chi equals the limit as S approaches infinity of the limit as R approaches infinity of the R minus 1th root of S epsilon times 1 plus epsilon to the power of R minus 1 over delta divided by S epsilon, which equals 1 plus epsilon to the power of 1 over delta. There we go! If you reinvest the farm income into more farms, you'll want the farm with the highest banana compound efficiency. The banana compound efficiency increases with the high banana efficiency and the low delta. If we look at the banana compound efficiencies of our farms, it's a bit weird because the banana efficiencies were small positive fractions, but the banana compound efficiency is more than 1. So to make them consistent, let's subtract 1 from our definition. After subtracting 1, the banana efficiency and banana compound efficiency of most farms are the same. Yep. For non-banks, they're always equal. Why is that? For non-banks, delta is 1. Let's pass this into our formula for chi. Chi equals 1 plus epsilon to the power of 1 over delta minus 1, which is 1 plus epsilon to the power of 1 over 1 minus 1, which equals epsilon. Yup, they're equal, alright. This calls for a second theorem. Let's call it the monkey bank theorem. When delta is 1, the banana efficiency and banana compound efficiency are equal. When delta is more than 1, the banana compound efficiency is less than the banana efficiency. Remember these two important theorems, they will be on the test. Let's understand this function a bit. I've graphed the plot of chi with respect to epsilon and delta here as the green surface. Chi is 0 when epsilon is 0, and increases with epsilon. When delta is 1, chi and epsilon are the same. When delta increases, chi drops off quickly. Here's the 2D graph of chi with respect to delta when epsilon is 1. And here is all values of epsilon and delta with banana compound efficiency of 1. You see, we need a really large banana efficiency to make up for only a slightly bigger delta. And if you're doubting my calculation skills, here's some code ChatGPT wrote to simulate banana farms. The formula prediction and real profit are ridiculously close. The difference is a bit bigger if delta is not fully divisible by R. Let's check out the real data. If we reinvest income into more farms, it turns out to be better to withdraw monkey bank balances after just one round, because reinvesting into new banana farms does more for you than the actual bank interest. Ironic that the monkey bank is actually the worst farm for compounding. Taking that into account, monkey bank is no longer the best farm. In fact, it's pretty bad. The best farm is now banana research facility with valuable bananas, and then the marketplaces. IMF loan is now the worst with only a measly 1.9% banana compound efficiency. But to be fair, we are ignoring its special ability to take loans. What's your excuse, valuable bananas? Keep in mind, banana compound efficiency is only the best metric if you spend all your income on buying more banana farms. If you want to buy some farms and use their income on defense instead of reinvesting into more farms, the banana efficiency is still a better metric to use. But valuable bananas is bad either way. Valuable bananas? More like invaluable bananas. Oh wait, that's still a compliment. Of course, we're still ignoring space efficiency and discreteness efficiency for both metrics, not to mention special abilities certain farms have. But valuable bananas is not super space efficient or cheap and doesn't have any special abilities. I think the takeaway of this video is that valuable bananas is trash. But there you have it. We've come up with two different measures for how good a banana farm is. The banana efficiency, which is income divided by cost, and banana compound efficiency, equal to 1 plus epsilon to the power of 1 over delta minus 1. We've also discovered two theorems. The fundamental theorem of bananas tells us that the banana payback is the reciprocal of the banana efficiency. And the monkey bank theorem states that for period 1 farms, the banana compound efficiency equals the banana efficiency, but it is less if the period is greater than 1. So to choose the right banana farm in BTD6, focus on banana efficiency and banana compound efficiency. Just steer clear of those valuable bananas. I feel like every sentence in this video is a sentence that no one has ever spoken before. But I hope you've enjoyed this video. Mathematics can be abstract and obtuse, but it can also be incredibly useful. Which banana farm is best is a question I've wondered for a while. To solve this problem, we went through the same steps of mathematical problem solving as you would in the frontiers of research. Trial and error, defining new concepts, plugging in concrete numbers, and of course, taking limits. Bananas and limits? Name a more iconic duo. I've included a link to the banana farm spreadsheet in the video description if you'd like to play around with it. Have a spectacular day. But if that's not good enough for you, greedy banana.